So this is the electric field. We can see that this is an electron and there are two positrons here. So we create this kind of electric field. Because they are of the same charge, so there will be no lines between them. And there are the different charges. This is one is negative, one is positive, so there will be lines between them. And we can increase, maybe just create more points. And we can set the charges. Let's say I reduce the charge. We could also increase the charge. It's fun. And we can set the charges individually, set the positron and the electron. So, also we can create an isosurface. So this will be the isosurface. That is to say that for each point on this connected surface, the intensity of the force is the same. Not the direction, but the intensity. That is the strength of the forces. This is the isosurface. And this might be useless, but I just find this kind of interesting. So to implement this, it's quite easy. Let's say this is an electron, and this is a positron, and this is also a positron. And let's also assume that the charges of this guy is 2, and the charges of this guy is 1, the charges of this guy is 1. So let's see, assuming we are considering this point in the space, what's the force? Let's consider there is an electron here. What's the force at this point, given the condition? It's simple. All we have to do is using the Coulomb's law, Coulomb's rule. So the forces will be, let's say the distance between this guy and this guy is r, and it's a vector. So the forces will be q1, q2. Q is the charge, so it's 1, and q2 is -1. And times the normalized r, the normalized direction r, divided by r squared, the length. So this is the force at this point between these two charges. So all we have to do is to also calculate the forces between this point and this point, this point and this point. So all we have to do is use the sigma to calculate all the forces between each of the points. This is basically the Coulomb's law rule, Coulomb's law. The forces is just QQ r squared and times the unit vector r. So what we are going to do is just create a volume, and for each of the voxel in the volume, we calculate the force. So we can have a vector field, and that would be the electric field. So let's take a look. So first I create a box, and then I create two volumes, one to store the intensity of the force, I call it density, as a scalar field, and another is a vector field called velocity. And then we're also going to prepare the electron and the positron. So I simply scatter some points inside the volume, and then I set the charge here. To set the charge, we could see in the point we have the charge. So for some of the points, I set them as electron, and I also set the charge, and I also set the positron also set the charge. So we collect all the points. And yeah, these are the electrons and positrons. We also set the group. And what we have to do now is for each of the voxel, we use a volume wrangle. This is simple VEX code. For each voxel, let's say we just loop through every one of the positrons and electrons. So we use n points, the number of points from the input one, connecting to all the points. And we just, for each voxel, we loop through all the points. And then first we check if it is an electron or positron, because we will flip the force if they are both negative or yeah. And then we just use and we just calculate the distance between the voxel and the input electrons or positrons. But there is one catch here. I divided by the boundary of the box because I want the distance to be normalized between 0 and 1. This is good because yeah, we kind of normalize our distance. And we calculate the forces direction, basically just minus the current voxel's position to the electron position. And then we can calculate the force. So we just add the force. We have the unit vector direction times the charge and divided by distance squared. And we set the force to the velocity field and also calculate the strength of the force into the density field. So now we have a velocity field here. So all we have to do now is to prepare some points. So I scatter some points on these points are positrons. So I copy a sphere to the position of the positrons and scatter some points on it. Just like this. Or copy to the, and then we can use volume trail. Yeah, we can see that we started to trailing along the vector field we have created. That's basically it. Yeah. Because we also store another field, this is the density, the strength of the forces. And we can use this to create the isosurface. So basically, we just use this convert volume to convert the volume back to the geometry by setting different iso value through a loop. So after the looping, we can see, wait a second. Yeah, we can see that we got different result. Yeah. Yeah, because we can see that, let me copy paste. Let me delete this. And yeah. Yeah, we can see that by setting different iso value, we can get the isosurface. So all we have to do is just using a loop and to loop through different iso value. One thing to notice is here I simply use the length to convert the force and store it into density. But this is not normalized. So I simply use the volume min and volume max. So to get the minimum and the maximum value in the volume, and then remap them into 0 and 1. Just a simple remapping function. So I can, when I'm converting back, I could just set this value between 0 and 1 and by a loop. So this will be the final result. Yeah, so that's the final result we can see here. We can play with, let's say, different charges And we can use this to create basically this is the same as the magnetic field. Yeah, so you can think of this as an Earth, and we have the North Pole and the South Pole, and we have the magnetic field between them. And just kind of fun to play with this. And it's really easy to implement. Basically, just all we have to do is just this volume wrangle. You just have to loop through every voxel and calculate the force. That's it. So I will share the HIP file in the description. If you're interested, just grab this file.